On this recording, we're going to do the same thing we did for the last recording, except this time we are going to trace fat through instead of carbohydrates. So remember the last one we traced a blood glucose all the way through. This time we are going to trace a 16 carbon FFA. Okay, so we got 8 carbon pairs. Again, we're going to count how many oxygens we use in electron transport chain and how many CO2s we produce. Okay, and I've already told you that the RER for 100% FFA oxidation is 0.70. So let's see if we can come up with 0.70. Alright, so when we go through fat oxidation, we start with an FFA, which goes through the activation step. And remember, we've got a 16 carbon FFA, so we've got 8 carbon pairs, and we have 7 bonds. Okay. Okay, so 1, 2, 3, 4, 5, 6, 7, 8 carbon pairs, and 1, 2, 3, 4, 5, 6, 7 bonds. Okay. And this activated FFA goes into the mitochondria. It goes through beta oxidation, and a carbon pair breaks off, makes acetyl-CoA, goes through Krebs cycle. So first let's talk about beta oxidation. We don't get any CO2 and we don't use any oxygen in the activation step. Okay. In beta oxidation, we do not produce any CO2. Again, we don't use any oxygen, but we do get hydrogen and electron pairs that go off to the electron transport chain. So every time we go through beta oxidation, we go through electron transport chain twice. Okay? But when we're talking about beta oxidation of a 16 carbon FFA, we go through beta oxidation 7 times, okay, because we have to go through 1 time to break each bond. 1, 2, 3, 4, 5, 6, 7 bonds. So times 7, okay, 14 times through electron transport chain. And then we end up sending 8 carbon pairs, or I should say 8 carbon pairs become 8 acetyl-CoA, and therefore we're going to go through Krebs 8 times. So for now, just keep this number in mind, 14 times through electron transport chain. Let's review what happens in Krebs cycle. Okay, so we're talking about FFA. Not glucose, so the intermediate step has nothing to do with this here. Remember, this CO2 is wrong. Okay, we don't get any oxygen directly, but we're going to get the oxygen from electron transport chain. Every time we go through Krebs cycle, we do get 2 CO2s. Okay. But with an 18 carbon FFA, we end up with 8 carbon pairs, so 8 acetyl-CoA. So we go through 8 times. So 16 CO2. As far as electron transport chain, we send 1, 2, 3, 4 pairs per Krebs cycle. Okay. But we go through Krebs cycle 8 times. So we go through Krebs cycle 32 times as a result of the hydrogen and electron pairs that are given off in Krebs cycle as a result of 16 carbon FFA. Okay, so let's put these numbers together. Oh, and again, you know, each of those carbon pairs is going to go through electron transport chain and use a half of an oxygen. Okay, so from beta oxidation, we went through ETC (14 times). From Krebs, we went through 32 times. Okay, so 46 times we go through ETC. Each time we use a half of an oxygen. So we end up using 23 oxygen molecules to completely oxidize a 16 carbon FFA. Alright, so we have used 23 oxygens. We are trying to come up with an RER of 0.70. So let's look at the CO2s. In beta oxidation, we did not produce any CO2. In Krebs, you know that we produce 2 CO2s, but with a 16 carbon FFA, we go through Krebs 8 times. So we've got 16 CO2. So this will be 16. This will be 16. You do the math and you're going to get 0.70. Okay? So we use 23 oxygens. If you go back to chapter 2 and you trace a 16 carbon FFA, you'll see that we end up with 106 ATP. 106 divided by 23 is 4.6, and this is the oxygen efficiency value of FFA. Okay, just to remind, this comes from chapter 2. We were talking about oxygen efficiency, and the oxygen efficiency for fat is 106 ATP. We use 23 oxygens, so the oxygen efficiency is 4.6 ATP per oxygen molecule. For carbohydrate, the numbers were 32 ATP, because we used a blood glucose as our example, and in the process we only use 6 oxygens. So we get an efficiency of 5.3 ATP per oxygen. Okay, so you can see that per oxygen molecule we get a lot more ATP. Okay, whereas with fat we get more total ATP, but it's not very oxygen efficient. You could see to get 106 ATP, we used 23 oxygens. We used a lot of oxygens. We relied very heavily on the electron transport chain. So that's where those numbers come from.